Welcome to the Castle webinar series. My name is Hani Abdel-Khalik, and my co-presenter, Dr. Ralph Smith from the Mathematics Department. We would like to talk to you today about our course development efforts here at NC State in the area of uncertainty management, an area that has become instrumental for Castle's mission. So just a little bit of background on this. About 3 years ago, I started thinking about having this course, and at that point I met Ralph through Castle, and it turns out that he's been doing this for a couple of years before that, and he was focusing in his course on verification and uncertainty quantification. So we start talking about maybe we should develop a two-course series so that we can expose people to both engineering and mathematical perspectives on uncertainty management, and we want to share some of these efforts with you today. So I'll talk first about the course in the Nuclear Engineering Department, which I'm teaching, and then I will give the floor to Dr. Ralph Smith here to talk about his course in the Mathematics Department. All right. So we'll be talking about uncertainty management techniques. The word uncertainty, you probably have heard it many times, and scientists have been focusing on calculating uncertainties for as long as they have been trying to predict natural or man-made systems. So when you are making any kind of prediction, you should be prepared to answer the question of how accurate your predictions are. And over the last century, people have mainly been focusing on experimental approaches to measure how reliable their models are. And what that means is that you build an experiment and you compare that to your predictions. And you take the discrepancy between the two as a measure of how accurate or how reliable your model is. Over the past 10-20 years, the scientific community has been getting really excited over this notion of replacing experiments with high-fidelity simulation. And the reason for this is the cheap computing power has become very cheap over the last 20 years, and we are now motivated to try to build models that are very detailed, and maybe they can help us replace experiments, or at least reduce reliance on experiments. We will always need experiments. But if that's the case, now you don't have that access to that many measurements. You have to be prepared to answer another question. How confident are you about your predictions? And that's where the subject of uncertainty analysis comes in to help you provide this confidence required by decision makers when they receive your input. Okay, so you can think of predictive science or computational science as a type of science that lies at the intersection of physics and engineering. Physics, as you know, describes how systems behave, but engineers need models that they can run accurately, efficiently, and confidently. So you see here the distinction between these three different key phrases. It has to be an accurate model, and with lack of experiments, you have to be confident about these predictions, to provide some measures of confidence, and also it needs to be done on an efficient basis, because engineers need to run these simulations many times as part of their day-to-day operation. So a computational scientist is somebody who must understand physics, must understand engineering needs, and it turns out he has to also understand mathematics, because taking the physics and rendering a computer model that engineers can use requires a lot of knowledge of calculus, linear algebra, probability theory, statistics, geometry, to be able to complete his job. And as I said, the quantification of uncertainty becomes an important objective here, as it provides confidence in the simulation results. So that's an overall 50,000 little feet of why uncertainty analysis is required in our discipline. So the first course is the one that's taught by myself in the Nuclear Engineering Department. It's 491, 591. These numbers mean this course is taught at the senior undergraduate level and incoming graduate students. So I taught this class first at the graduate level, but I thought it's very important to expose undergraduates also to this type of analysis, because now it's becoming a requirement for all engineering analyses. And by the time they graduate, it will be nice if they already have some background on it. So we start with the definition of uncertainty quantification. We talk about types and sources of uncertainties, and we focus a good part of the course on background and related topics. As you will see later on in the presentation, there are a lot of mathematical topics that are required to understand UQ, such as linear algebra, Bayesian probability theory, sampling techniques, sensitivity analysis. We go through each one of these topics as we need to get a good understanding of the whole subject area. And then we talk about how to do UQ via sampling techniques, via surrogate-based techniques. I'll give you an idea what that means. And most importantly, I like to share with the students the recent developments in the UQ area, because when we talk about recent developments, we're addressing the challenges that we are currently facing. And that hopefully motivates them to think about outside the box and about what's needed to address some of these challenges. Okay, my usual disclaimer, I have a mathematician
I like that.
sitting right next to me here. I believe more in intuition, you know, and especially that we're engineers, we have to run these models, we have to use the best mathematical tool available. You might have a very good theory, but in the practice not very good. You might have a very practical theory, but it's not very accurate. So intuition has to really become primary. And I think of mathematics as a secondary objective. It's not important, but it needs to go hand in hand with intuition. So because we have two courses, one on math and one on engineering, I thought it would be okay or reasonable to, you know, give the students the engineering perspective, which focuses a lot on intuition, and then also in the math course they can be exposed to the rigorous treatments. And that's not belittling at all the role of mathematics, because without that rigor treatment you can't really make these statements that you're really confident about using whatever analysis you are employing in your model. So I just have this interesting comment here. If you breathe epsilon delta type proofs, you'll definitely be disappointed in this course. But I'm hoping that you can still come and learn about how engineers employ these methods in real applications if you are a true mathematician at heart. And the course assumes some little background from calculus, probability theory, matrix algebra, and regression. Typically the same kind of knowledge that's offered to undergraduate students in any engineering discipline around the country. All right, so uncertainty quantification, we start in the course by explaining what is UQ. There are several definitions for it. I overview some of these definitions with you here. It measures reliability of a model prediction. You can think of it as measuring the distribution of all possible events. And you can think about it as a way to provide quality measure for your model predictions. And we go over each one of these and give you some examples. And my favorite definition of UQ is really, it's what it pays scientist salary, because obviously if we know all the answers, we don't need to hire these interesting people. So uncertainty management. What I mean here by the word management, it really means three things. It means uncertainty quantification, UQ. It means sensitivity analysis, SA, and it means data assimilation, DA. UQ simply measures all possible outcomes. So if you are analyzing a certain system, you want to know all the possible things that can happen if you perturb the system in a certain way. SA, on the other hand, tells you the key sources of uncertainties and their contribution to total uncertainty. Why is that important? Because engineers, if they know 90% of the uncertainty, let's say, is coming from a given data that's input to the model, then they can go and invest into improving the quality of this data. So they can prioritize their efforts here. Finally, DA, data assimilation. How do you employ measurements to reduce uncertainties? So as I said, the uncertainty quantification tells you how confident you should be in the model. But we will still need experiments. Hopefully not as much as we did in the past, but these experiments, however scarce they are, they can still be used to advise the model on how to reduce these uncertainties that were quantified by UQ and explained by sensitivity analysis. So these three topics here go hand in hand, and you really need them all to be able to do an effective uncertainty management. Here's a graphical display of what that means. So on the x-axis here, you can think of this as your input parameter to a model. since we're nuclear engineers talking here, we can think of this as a cross-section for a given material, given reaction type. And then the output response could be a detector response, or is the reactor critical, K effective, for example. And the blue line indicates a model that relates the output response with in terms of the input parameter. And as you can see, there is two distributions, one for the input parameters, the one in the solid red. This describes your prior knowledge about your input parameters. Where did you get that from? You called an experiment and he did some experiments for you, and that's the result that you got. So the first step of uncertainty management is UQ. That means you take that uncertainty curve, or we call it a PDF, probability distribution function, and translate it into a PDF for the output. And how wide that PDF will be a good measure of how confident you are about your answer. So this is the first step. The second step is, if we have some measurements for this output response described by the bold solid red curve on the y-axis, can we use this information to improve our knowledge, our prior knowledge about the parameters? And as you can see here, it's as if you are inverting the model, going from the y-axis and you're trying to answer the question, what x's give me that y? And hopefully what you will get is something that is narrower, meaning that it has a lower uncertainty associated with it. So this last step is called the data assimilation step. Sensitivity analysis, it's hard to explain it here. You can think about it as the slope of the curve at the point where the input parameter value and the output response meet. If we have more than one parameter, you will start thinking of a multidimensional graph for this. And we will be asking questions, how much uncertainty is coming from each one of these parameters. Okay? So UQ methods, a good way to think about different UQ techniques is that we have some simulation code, a black box usually, and the easiest thing we can do if we are interested in understanding the distribution of all possible events is that we just have mini samples for the input parameters, and we run the code multiple times and we do statistical analysis on the results. If the simulation code is expensive, then we have to resort to this other approach, a surrogate model, usually developed using sensitivity information. And even with the surrogate model, it turns out that developing the surrogate model is also very expensive, but once you build it, it's very efficient to execute. You still have to do some kind of intelligent sampling strategy to reduce the number of samples, because most of engineering problems, the number of samples required are very, very large if we just do a brute force type approach. And of course, we have to answer the question of, is the surrogate accurate? So in this research community right now, there are people who are mainly working on addressing that question, is the surrogate accurate? There are some other folks that are working mainly on how do you do intelligent sampling when you have a very large input parameter space. So I'm going a little bit too slow here, but here's some of the jargon that we are exposed to in this course. You probably have seen some of this before, but we go through all these different concepts in the class as much as we need. We can't really obviously cover them in a comprehensive way, but we take what we need from them to give you a good overview of the UQ methods. So the course pie chart, I like to think of it as three different sections: a linear algebra section, a probability theory section, and a reduced order modeling section. Linear algebra, it turns out it's the most important tool, because no matter how complicated your model is, at the end of the day, it gets written in a computer code, which gets executed on a computer, and usually in the form of matrices. Probability theory, we also spend some time talking about probability theory to describe how confident we are about results. And reduced order modeling is important, as I showed you in the previous slide. When the code is very expensive to run, you must do some surrogate modeling construction. And at the end, we put it all together in some demonstrative example. So I'll just give you a couple slides about each one of these just to show you why we need them. And this other pie chart here shows you, from a research point of view, what we can do today with these methods and what we would really like to do to address a realistic engineering problem. So there's a lot of room for research and development, which I'm hoping the students can take from this course. So I start with linear algebra and I show you that it really can be described by Ptolemies Theorem, something that was developed 2,000 years ago, and it provides a measure of how correlated information can be. And it's really using this simple graph here.
And that's from your home country, isn't it?
That's right.
Okay, I've got to put in a plug. Yeah, that's...
He actually did that when he was in Alexandria. That's where I was born. So you can understand now why I'm biased.
Very good.
And I can actually derive Pythagorean theorem from Ptolemy's theorem. So why do we need linear algebra? Turns out linear algebra can help you find patterns in complex systems. So I usually give these to the student, these numbers, and I tell them, can you find a pattern here? And it's unless you're a walking computer, you can answer this question, because it's really very difficult to look at these numbers and come up with some kind of pattern. This is showing you the number of people and how much, let's say, beverage they're consuming after different hours. But if I give you these numbers, it's much easier to see a pattern. 1, 2, 5, 2, 4, 8, 10, 4, 8, 20. So it's like the same pattern 1, 2, 5 is being repeated, but with different number of people. If I show you another case, you also see that there's a very easy pattern here, 2, 3, 7, 6, 9, 21. So 2, 3, 7 is the recurring pattern here. So all I did, the first example, just added these two and came up with this. So that means really these numbers have two patterns in them, 1, 2, 5 and 2, 3, 7. You can think of it physically as 1, 2, 5 are the light drinkers and 2, 3, 7 are the heavy drinkers. So that's why we need linear algebra, because it helps us rifle through a lot of data and find some important patterns in them, which interestingly enough becomes a very important component of UQ. Okay, so this is, let me just go through this. Now the next subject is the probability theorem. The motivation for this is that really you don't really understand something unless you can describe it with a number. And probability is probably one of the most talked about subjects in the scientific community. But you'll learn in this course that really describes two different things that are entirely different from each other, but both are called probability. One of them is the frequency. If you toss a fair coin, there's 50 chance you'll get heads. But there's the other one which we need a lot in, and when we talk about inference and data assimilation, is the degree of belief. So a question is posed a little differently if we use the coin toss. Given a coin of unknown origin, you don't know if it's fair or not, and you toss it twice, and you got tails in both tosses. Can you make a statement about how fair this coin is? What is the probability that you can get hit or tail in the third toss? Another example, a realistic engineering example, you measure thermal conductivity, let's say 100 times. And after the 100 times you want to make a statement, you believe that the probability of finding the true value for K is somewhere between K1 and K2, let's say is 90%. That's the kind of statements that we want to make with the degree of belief interpretation. And interestingly enough, the way to handle probability based on frequency is very, very different than probabilities based on degree of belief. So, we still have probably a few moments.
Yeah. And
so,
we'll start with K2. So.
Okay.
Yeah,
so with the probability, we go back to early last century. Cox, he came up with all these different basic rules to describe probabilities. And qualitatively, we think of probability as unlikely, probably, surely. So he said, let's assign numbers to these things. And if you think something is more probable than something else, then it should have a higher number associated with it. And these rules were taken for granted, considered obvious, and thereby not necessitating proofs. Okay, so here's an example. You measure the thermal conductivity, and you say, I think 90% it's between K2 and K3, and 10% it's between K1 and K2. So an important question that after you provide this data, when the engineer will ask you, what value should I use in my analysis? So we addressed that in the course. The next subject is combining the PDFs, because we gather information from multiple sources. You can think of this as multiple experiments. How do you gather all this information together? So let's say you have two different distributions representing either frequency or degree of belief about probability. And you obtain them from two independent sources. They're not influencing each other at all. How do you combine them in a single PDF? Here are some simple examples. You send two pollsters to estimate Republican-Democrat split in your hometown. How do you combine their results? Degree of belief. You measure the unknown value for thermal conductivity using two different experiments. How do you combine these two different values? And it turns out you actually use two different mathematical approaches. If it's frequency interpretation, you simply add the two probability distributions and you scale them by the population size. I will go quickly through this. And for the degree of belief or interpretation, on the other hand, it's much more different. So if you look at the right side of the screen, you hire two experts to measure K. And the first expert told you 20% it's in A, the A region, and 80% in the B region. And the second expert told you the same thing. Wouldn't that give you more confidence than your real value is in B range? How about the other case on the left? They give you opposing opinion. So what do you think your degree of belief should be? And I always give this simple example in the class. If you're in a foreign country and asking for directions, you ask the first guy, he tells you go this way. Then you ask another guy, he tells you the same thing. So you have more confidence now. So when we combine these PDFs, we should be able to reflect that into the method used to combine them. But if these two guys give you different answers, then you have to start from zero again. Ask another guy. So it turns out to combine PDFs that are described by degree of belief, you have to multiply them, and then you have to normalize it to 1 after that, as opposed to adding them up when we were talking about frequency interpretation. So I talk about these two different approaches and show you how they're used in handling an engineering problem. Okay, next thing is inference. I told you at the end is we still have some measurements that we will rely on to improve our knowledge about our uncertainties. This step is called data assimilation. In the probability and statistics literature, it's usually referred to as inference. So the motivation is that you set up an experiment to measure unknown physical constants, and the measured value is usually different from the true value, which you're after. And you are asked to answer this question. If you are making these measures, could you give me your best estimate about the true value? Okay? And the PDF that describes the distribution of measurements around the true value is called a likelihood function, and I'll give you an example of what that looks like in the next slide. So here's one of the most common PDFs used to describe measurements. Let's say here x0 is the true value for thermal conductivity. And then you ask an experimentalist to measure that. He will not measure exactly x0. He will measure a bunch of values. When they are statistically distributed, they will look like this PDF. So more measurements will be done around x0, and far less measurements will be done 3 sigmas away. Okay? So now, in reality, we don't know x0, but we know the measurements. We make the experiment a couple of times, and then we ask the question, could we provide an estimate for x0? So that's called inference. So it turns out to do inference, it's really very simple. We define this PDF, P of x given x0. It's defined as, if we know the true value x0, what is the probability of obtaining a given measurement x? But somebody could look at this equation and say, given x measurement, what is the probability that I find the true value around x? So you can look at these two, this equation in two different ways, and that's mainly the difference between doing prediction of your measurements or inference from your measurements about your uncertainties. So here's an example. The forward problem, you know the true value, but you don't know what the measurement's going to be looking like. So you use this PDF to estimate what the measurements should look like. But in the inverse problem, on the other hand, so in this case, the measurements are unknown. In the other case, the measurement is known. You make a given measurement, and you want to know what is the probability you find a true value around x, and it's described by this distribution. So this distribution says there's a high probability you will be around x, and very lower probability you will be very, very far from x, which is to be expected. So inference, in reality, we don't run just one experiment. We run a bunch of experiments. So here's experiment 1, 2, 3, 4. And as you learned early on, these are all degree of belief. So how do we combine them? We multiply them by each other. And it turns out you get something that looks like this if you start with Gaussian PDFs. Very nice shape, another Gaussian. And then you use that to make an inference about what your best estimate for the true value of your input parameter. That's really the basic gist of these methods. I can skip that here. Maybe, yeah, let me just point this out quickly. We talk about, if my model is linear versus nonlinear. You see the linear model, if you start with the Gaussian measurements, you end up having Gaussian, what we call posteriori uncertainties, because it's linear. But once you have a nonlinear model, you can start with Gaussian and you end up with something else, which is more the realistic case that we find in engineering problems. So we discuss how could that impact the analysis that we use, and how can we try to address it and make it more efficient. All right, uncertainty quantification now. I want to talk about quickly the sampling approach and the surrogate approach. So as I said before, the idea is really simple. You start with some samples, you run your model, you have your results for the responses, and then you do some histogramming for them. You call this a PDF. And there's another form to display the data called CDF, that we also, cumulative density function, that we will describe in our course. So it's really simple approach. But an interesting question that I try to address in this course is why sampling works. People have been using sampling techniques for a very long time. But interestingly enough, it was just late 19th century when they discovered why it works. And so I go over this integral equation where you're trying to calculate the integral of h of x times f of x, and f of x is a PDF. Turns out that you can evaluate this integral by simply sampling x according to f and calculating what h of x is equal to, and then you just average the values. And this estimate approaches the correct value as 1 over square root of n, which is probably the most powerful statement about sampling techniques, that you will always reach the right answer, regardless of what the model looks like, regardless of how many parameters you have. It's only a function of the number of samples you use. So the more samples you use, the better confidence you get in your results. So we use this to start talking about important sampling, which I referred to early on in the presentation. A lot of research goes on how do you make intelligent samples when your model is very, very large. And the idea is really very, very basic. If you look at the function on the right, h of x divided by w of x, it's almost like a flat function. If you sample this function, you'll probably get a better estimate of the integral than if the function was widely varying as h of x on the left-hand side. So people think of this, if I want to get a good estimate of my integral, I can just simply divide my unknown function, the complex function, by another function, which is very similar in shape. When I divide them by each other, I get something that's very close to a step function, which we know we can calculate its integral using just a single sample. So that's the basic idea of important sample that people have been using in uncertainty quantification and also in other mathematical modeling techniques. So we talk a lot about that and describe different methods to do that. So last thing I think I have in my presentation today is just to talk about sensitivity analysis. I showed you this picture before, but I did not really say how do we go back from our measurements back to our input parameters. So if the model, the blue line, is just a simple function, you can easily invert it. For a given y, determine x. But if the function is implicit or it's a black box, it's not easy to do that. So what people do is they build the so-called surrogate model, which is simply an approximation of that blue line. And as you can see here, I use the simple first order surrogate to describe the response variations of parameters. So using that model, you can take the measurements, which is measure the solid red graph. You take that and you project it back in terms of the input parameter uncertainties. And that's very simple to use if you have just a first order type surrogate. We discuss when this works, when it doesn't work, or when you have nonlinear behaviors and methods around that. So we describe sampling techniques to get sensitivity information. We also describe some deterministic approaches like finite difference and adjoint methods. And we show how the sensitivity information can be employed to build your surrogate model that you use to invert your model. So here's an example of what of the kind of project that I'll give you at the end of the semester. If you have a core model, the far right graph on the bottom, that shows you a quarter core model. Each one of these little squares is an assembly As you can see, the assembly has a lot of pins in it, and each pin has a different composition. And the cross sections, which is the basic nuclear constants used in any nuclear calculations, look like the graph on the far top left corner. And what we're interested in is calculating, let's say, K effective. Is the reactive critical? And I want you to make a statement about how confident you are in your prediction. So how do you take uncertainties in all these cross sections and propagate them through different models, going from pin cell models, lattice models, and core simulator models to come up with this uncertainty on the results. So that's the practical example that we give in this course. And some of the results that we should see is something like this. Like the top left corner shows you the uncertainty in K effective. Here in this graph, this is from some old results showing 700 ppm roughly the uncertainty due to cross sections. The graph right next to it shows you how this uncertainty is attributed to different cross sections, uranium-238, plutonium, gadolinium, etc. As I remember, I told you that we need sensitivity information to identify the key contributors to our total uncertainty. So these are the kind of things that we will be calculating and looking at and analyzing and trying to relate to our engineering understanding of the system. So this is really everything I have. I hope I didn't go through this very quickly, but if you have more questions after the question session here in this webinar, you feel free to email me. Now I want to give the floor to Dr. Smith. He will talk about his course.
All right, very good. Thank you, Haney. So just to set the tone, and I'm going to kind of repeat some of what Haney's talked about. When we're talking about predictive science, we're basically thinking about components, all of which involve uncertainty. And I'm going to see if we can, yeah, I was wondering if there's an arrow. We're not going to find that, so we'll talk to it. But experiments, models, numerical simulation. Quite often we think of numerics as basically deterministic. However, we worry about things like convergence. As we get into exascale, we also start to worry a lot about uncertain aspects, such as bit swapping. So just to point a little bit at where this uncertainty comes in, and I realize this is a Castle group, but I'm going to show examples that are, I think, very much in the news, and this is stuff that we'll show the class because all you have to do is turn on the news and you start to hear about this. But for example, on the bottom left, a big deal here in Wyoming where I grew up is fracking. And the thing that's really hard on hydrology or this type of geology is you have extremely limited numbers of experimental measurements. Drilling wells is expensive, often prohibitive. There's uncertainty all over the place. On the bottom right, you've got uncertainties in the models, and we talk about climate models. We talk about nuclear design in the context of Castle, but one of the things that's interesting in the climate model is you've got very coarse grids when you discretize the Earth. And then you're having to interpolate between these things because your grid may be on the order of 20 kilometers. Turbulence in the air may be on the order of meters. So that's where some of the uncertainty in numerics comes in. And then Haney was talking about quantity of interest, and just to give it a very good example, on the top right is a Katrina trajectory. And the quantity of interest there might be expected landfall, very simply. So in the course that I've been teaching, the number is 797 just because I developed it for 3 times under a special topics course, and we're putting this in as a early graduate course. Some of the topics we'll talk about are just an overview of topics where uncertainty quantification is critical, because as Haney said, it's really important that students see that this is emerging science. It changes, in some cases by the year. It's very, very topical. Obviously, we have to talk about random processes, probability. We do a little bit of verification. How do you know that your numerical code is giving the correct answer? And then we talk about frequentist techniques, Bayesian techniques, uncertainty propagation. One of the things that we complement, and I want to get across that these 2 courses are very, very complementary. And so we highly encourage students to take both. I hope I don't disappoint Haney in the sense that there are no delta epsilons in my course at all. It's very practical. We're trying to solve problems. So we'll talk a little bit about stochastic spectral methods and sparse grid methods as well. So just to give a flavor, and this is going to be a lot of squigglies, as some of my friends would say, but the idea that Haney was talking about with model calibration and sensitivity analysis, can be easily portrayed with a very simple HIV model. Now, it's simple in the sense that it's 6 coupled ordinary differential equations, and the thing to take away on the bottom is there's a lot of parameters. It looks like a lot. Some of these can be measured, some of them can't, all of them are uncertain, and this is actually very simple case that we can use to illustrate some of the methods in a course. And I'm just going to keep pointing back to what Haney was talking about. It involves inverse problems, which is given measurements of our variables T1, T2, etc., can we estimate parameters? Sensitivity analysis. Haney had a beautiful slide showing that it's really the slope on your input-output graph. As you start to vary those parameters, how do the outputs that we measure vary? And one of the really important questions that we answer in both classes is, among this set of parameters, are there some that are tremendously insensitive, and therefore we don't need to worry about the values so much? We talk about Bayesian estimation, metropolis algorithms, MCMC, maximum likelihood estimation, and so on. So again, I think what we want to convey is that these two courses are very, very complementary, and ideally, I think students would love to have both, and this is what we're trying to take to the community with both. So just to get a little bit more detail on what we'll talk about for the Bayesian estimation, in the frequentist perspective, parameters are fixed but unknown. They're deterministic. In the Bayesian, they're random variables. They have densities, and Haney talked about this. So the fundamental aspect of that is Bayes' relation, which relates the likelihood, which is the probability in a sense of getting observations given parameters. Pi naught is the prior, that's whatever prior information you have. And the object on the left is what we're trying to estimate. It's the posterior. What is the probability of getting parameter values given observations? The catch on Bayes' formula is this integral over RP. In the last example, P was 18. In the nuclear problems, P can be 1,000 or higher. And so even with the sparse grid techniques, you're not going to be able to do that integral. So the idea here that Haney talked about, and I'm going to go into a little bit more detail, is can we approximate that posterior by sampling from a similar distribution, a known distribution called J on the right, which is called the proposal, and have a law so that as we sample, it's going to converge in probability to what we're looking for. So the way that you would look at that is we're going to try and increase our likelihood. The pi of y given q is our likelihood that Haney mentioned. So if I take a sample q1 that increases the likelihood, I keep it. That's the black dot. If I take another sample q2 that further increases that likelihood, I keep it. Now, if I take a sample q star that decreases the likelihood, you accept it with a certain probability. And this is the essence of the metropolis algorithm. And this has been improved in many senses over the last 10 years by work by Harjo and his group in Finland. Dream is another version of this that Higdon and some of the group at Los Alamos and others have looked at. And what these algorithms have done is taken this type of sampling technology and made it very, very feasible for engineering, mathematics, science problems where you can easily have in excess of 1,000 parameters. You can have complex and coupled multi-physics codes that can take days or weeks to run. And I'm going to keep highlighting for these days to weeks to run, the reduced order surrogate models that Haney talked about are critical. So here's what you would get out of one of these things. You're sampling. You get what are called chains. And so I just illustrated 4 of the chains on the left for the HIV model. And from those, you're going to construct PDFs or densities. There's no assumption of normality here. You're constructing it for whatever it is, whatever the model tells you. Now, there's some big issues that we try and convey to the students. Namely, you're talking about convergence and probability. And often in the literature, this is calling burning in. But when you have only 100 samples from a large nuclear code, hard to convince yourself that's burned in. And the method we talked about on the previous slide, Dream, is massively parallel. That's an advantage of it. There's significant challenge for complex and coupled models. So this, again, requires the reduced order models that Haney was talking about. And this is something we convey to the students that this is ongoing research. This evolution to massively parallel architectures is ongoing research. But the advantage with some of the software like DRAM is we can get students involved in it very quickly and convince them that in a sense, you can treat it as you would any of the MATLAB or package-based optimization codes. They're very comfortable calling optimization codes. Here, what we would say is you're calling these Metropolis algorithms in the same way. All right, so for this example, we've calculated densities, and then we would talk about propagation techniques. And again, some of this is analogous to what Haney talked about. There's direct evaluation for linear models. And something that we always point out to students is linear is not with regard to the states, the T1, T2. It's with regard to the solution dependence on the parameters. And this is a kind of a change in thought from what a lot of at least the math students and many of the engineering students are used to. We'll talk about perturbation methods and when they work and when they don't. And then the sampling-based that Haney talked about, as well as stochastic spectral. So just to illustrate what will happen on the sampling-based, they're very simple. You sample from the elements in the chain, DRAM, DREAM, whatever you've used in your chain. As Haney pointed out, it's independent of the number of parameters. That's a huge advantage. Now, the problem is, in many cases, parameter sets are correlated. If you increase one parameter, you're increasing another. This method does not depend on that. It does not require Gaussian densities, and it actually is optimal for large parameter dimensions. So the illustration on the bottom left is there's 6 samples from my chain. I use that to construct what we call prediction intervals, which is shown in the middle and on the right. And the data is the dots. The darker gray is the confidence interval. That's how good is your model based on that fit. And then the prediction intervals are what we really care about in engineering and mathematics. And that says, if I take another sample, where do I expect it to go? So in the middle, I've plotted a 95% prediction interval that says 95% of the data should lie in there. And you can see quickly that's roughly true. Now, on the right-hand one, it points out that this is very, very non-Gaussian. And this is another illustration of what Haney pointed out, that for these non-linearly parameterized distributions, a Gaussian input can lead to an extremely non-Gaussian output. And all of the methods that have the assumption of Gaussian at various points are going to be limited if you're getting into this kind of output. Now, the 1 over square root of m is independent of the number of the parameters, but it's relatively slow. And to illustrate that, you need 100 additional evaluations to gain a place of accuracy. For very, very large scale problems, this may or may not be feasible. Again, back to the reduced order models. Or we can talk about the stochastic polynomial methods. Stochastic clarification is often called polynomial chaos. This goes back to the terminology of Wiener when he was actually looking at physical models for chaos. It's a bit of a misnomer in the sense that we are not dealing with chaos, but the term is held. There's stochastic collocation, which is applicable to general densities, discrete projection. All of these require mutually independent parameters or a transformation to get there, and that's something we talk about. And if you're starting to get to moderate dimensions, say 6 through 50 dimensions, you're probably going to have to get to sparse grid techniques. So we'll talk about that. So just to give a flavor of the stochastic collocation and a few more equations. Got to get some equations. There's no delta epsilons here, but I've got to do a few equations. Let's just think about a prototypical ODE system. HIV model, this can model, for example, the species equations in a simulator in some cases. But I'm just thinking about an ODE model where I have parameters Q. And what we do is we approximate the solution to that by decoupling the time component and the parameter component. For those who are familiar with Galerkin methods or finite element methods, this is a similar expansion where we're representing, instead of, for example, the spatial behavior, we're representing the random behavior. Now, for collocation, we would generate M samples, and I illustrated that on the right, from our parameter space. And we would enforce the condition that the, quote, true solution equals the approximate solution. Okay, so I've got a solution going through that. I want my approximate solution to equal the values that I sampled. All right, so all we do is just write down the system that goes with that, and it's a matrix system. And we can make that a square matrix system. It's called the Van de Waals system. The problem is it's typically very, very ill-conditioned. Even for numbers like 10 by 10, it's often tremendously ill-conditioned. So the way we would address that, and this is what's typically done in stochastic collocation, and this is the last slide of squiggly, so we're just about done with this, is to say, all right, For that matrix system, let's employ Lagrange polynomials, which are 1 if k equals m and 0 if it's not. It's just the Kronecker delta. So what that does is it takes all of the off-diagonal elements to 0, and it simply enforces this relation, u sub m is equal to the true solution at that point. All right? So that's equivalent to just solving our differential equation for m different parameter values. And it's really, really important to note that this is not intrusive in the sense that you employ existing codes, you're not modifying the codes. Haney pointed this out, and I'm going to reinforce it because it's a huge deal. We don't want to go into castle codes or climate codes or whatever code somebody has spent 1,000 man-hours developing and say, you have to modify it. We want to be able to sample from it. And that's what stochastic collocation does. Now, looks really good. It is really good until you go to multiple dimensions. So if I take the interpolation on the right and I say, let's go to 2D, and I'm going to just take a tensor product of my points. That's really intuitive. And that just says, I just multiply the 2 points. I get a grid that I show in the middle. And here I've got 9 points for each dimension, so I've got 81 points for 2D. Not a big deal. In 3D, I'm not going to embarrass myself and try and figure out what 9 cubed is, something like 9 cubed. And you start saying, oh, that's still not too bad. In 40D, you have 9 to the 40th. And you've got this explosion in the number of required evaluations. It's exponential growth. And this is prohibitive beyond about, 6 or 7 dimensions. This is the curse of dimensionality that people talk about. So the idea on that is to say, all right, we can approximate the results in that middle grid with the same accuracy with a reduced number of points, and this is the essence of sparse grid techniques. So the grid on the lower right has far fewer points than the 81 in the middle, and yet it has provably the same accuracy. And I guess we do actually worry about the delta epsilons, we worry about the accuracy, but the whole idea of sparse grid techniques is we can get the same accuracy for far fewer points. And for those who've heard of Smolyak quadrature or Smolyak interpolation, this is it. So this is the essence of the sparse grid techniques, and what we'll do is we'll take our students through that as well. So we're basically at 50 minutes. I want to leave time for questions. So just these are concluding remarks, I think, and I can speak for both of us, that the thing that is really exciting about uncertainty quantification is, as Haney pointed out, it's job security for all of us in many ways. It's inherent to essentially all the large-scale problems that we're looking at today and will look at in the future. It requires a synergy between statistics, probability, numerical analysis, and domain sciences, and I've forgotten several there. And we try and convey to the students it's a very active research area. This is a great area to then go on and do research. You have to be worrying about reduced order surrogate models for many of these things. And from an educational perspective, Haney and I are coordinating what I think is a really neat and important coordinated curriculum for engineering, math, science, statistics, biology students. I'm really excited to be at a place where we're actually, I think, able to lead on some of the development on that. And what we want to do at this point is be working with other institutions to combine our resources, get this into the community where we can use it the best. And so just a kind of a concluding remark, and I always point this out to the students, the famous or infamous hockey stick that has been in the news all over the place on climate change, for many years, it's the top right one, and what it shows is this spike in temperature, roughly at the same time there's a spike in CO2 levels. For many years, it was presented without uncertainty bounds. It was simply the stick itself. When you start to put uncertainty bounds onto it, it's still an increasing temperature, but it's a lot less obvious. And so for these very, very large engineering science problems, uncertainty quantification is critical. So I think with that, let's go ahead and conclude and open up for questions.